Okay, so in the last video, which was the first of from 1110, uh, I explained the whole rationale behind Taylor Maclaurin series, and we even found the sigma notation representation of sine x as a Maclaurin series. So let's go ahead and jump in, and let's actually find cosine. Okay. Now this is the formula, right? So if we want to find cosines Maclaurin series, remember Maclaurin is the one that is centered at 0. So notice that there's no x minus a here. It's just x. So it's x minus 0, right? And it's each successive derivative evaluated at 0. And actually that shouldn't be k right there. That should be the nth derivative. So we're all consistent. So let's say we have y is equal to cosine x, okay? Well, the original is going to be, let's call it f of x, is cosine x, and therefore f of 0 is cosine 0 or 1. We know that the first derivative is going to be negative sine x, and the first derivative at 0 is going to be 0. We know the second derivative is going to be negative cosine x, and therefore the second derivative at 0 is going to be negative cosine 0 or negative 1. We know the third derivative, and of course since this is, patterned, you can go ahead and just assume that it's going to continue in the same way. That's going to be sine of 0 or 0. So the fourth derivative at 0 is going to be 1. The fifth derivative at 0 is going to be 0. The sixth derivative at 0 is going to be negative 1. And the seventh derivative at 0 is going to be 0. And on and on and on and on and on and on and on. Okay? Now, we know that, in sigma notation, it looks like this, right? And it's, the nth derivative at 0 over n factorial x to the n. But if it's elongated out, what it looks like is, the original function at 0 plus the first derivative at 0 over 1 factorial. I guess this is over 0 factorial officially, right? Times x. And then, of course, the second derivative at 0 over 2 factorial, and that's x squared, and on and on and on and on and on. So, what we have here is, well, every other term is 0. So, the first degree term, the third degree term, the fifth degree term, the seventh, we don't have to worry about those, right? What we have here is we have, in terms of cosine, 1 minus, and of course we're not going to worry about this one since it's going to be 0. We're going to have x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and on and on and on. Well, that means that if cosine x is equal to that, then cosine x is going to be equal to what? Well, let's go ahead and put it back into sigma notation. It's n is equal to 0 to infinity of negative 1 to the nth of x to the 2n over 2n factorial. And that looks awfully similar to sine x. And all of a sudden, we're thinking to ourselves, isn't cosine just the derivative of sine? So did I have to go through all of this mess, or could I have just taken the power series, the Maclaurin series for sine x, and just taken the derivative? That is a very good question. So let's go ahead and look at that right now. Okay, so we know that sine x, right, when it is done into a power series, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot, 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 dot. And of course that is sigma n is equal to 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, well let's take the derivative. Cosine, okay, what's the derivative of x? Well, the derivative of x is 1. What's the derivative of x cubed? Well, it's 3x squared over 3 factorial, and this is 5x to the 4th over 5 factorial, and this is 7x to the 6th over 7 factorial, or what we have here is n is equal to 0 to infinity of negative 1 to the n of 2n plus 1 x to the 2n over 2n plus 1 factorial. Okay, you ought to recognize that there's a little bit of simplification that can be done. That's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And using our simplification, not just in the specific, in the numerical factorials, but in general over here, I recognize that 2n plus 1 factorial is 2n plus 1 times 2n factorial, so the 2n plus 1s can cancel, and you're left with that. Well, isn't that exactly what I got when I did it by the Maclaurin formula? And the answer is yes, okay? So you could have just taken the derivative of sin x, but, you know, always a good idea just when at the very outset to just sort of practice these methods. And of course, basically taking the derivative here has confirmed that my work in the previous step was indeed correct. Okay, well, I got another question for you. Let's say we have f of x is equal to e to the x. What is the Maclaurin series for e to the x? Well, if there's one thing that I know, it's that e to the x's derivative is e to the x, and its second derivative is e to the x, and its third derivative is, guess what, e to the x. So I know that no matter what derivative I'm talking about, it's going to be e to the x. So no matter what derivative I'm evaluating at 0, it's going to be e to the 0 or 1. Okay, well that means that e to the x is going to be, you know, the original function, the 0th derivative, I guess, evaluated at 0, so 1. And then it's going to be the first derivative evaluated at 0, or 1. And then the second derivative evaluated at 0, or 1. And then the third derivative evaluated at 0, or 1. Okay? And it's going to go on like that for a while. And then basically what we have here is x over 1 factorial. And you don't even have to put it like that. You can just put it as x squared over 2 factorial plus x cubed over 3 factorial, blah, 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 blah. Okay, well that was easy enough, okay, and basically you can put that into sigma notation like this. You notice that it's just going to be x to the n over n factorial. Okay, well what happens if I take the derivative of both sides? Because if this is indeed e to the x, when I take the derivative, it should be functionally the same. So let's go ahead and see if it is. Let's go ahead and take the derivative of the left side, and it's e to the x. Take the derivative of the right side. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 is x. The derivative of x cubed is 3x squared, so it winds up being x squared over 2 factorial. And so basically what happens here is it is exactly the same, it's just that everything has just shifted over one term, okay? But it winds up being an identical sum because all it does is just add 0, but it's still going off to infinity with exactly the same terms. So the property that we recognize in the original function e to the x, now, i.e. the fact that each of its derivatives is the same as the original, is true also for this power series. And that's significant, okay? So we've gone through and we've derived the Maclaurin series for sine x, we've derived the Maclaurin series for cosine x and checked it by taking the derivative of sine x. We've derived the Maclaurin series for e to the x, and we've done a couple of the power series as well by manipulating existing power series when we were talking about our friend 1 over 1 minus x. So at this point we've arrived at kind of, a handful or a few more of power series that should be recognizable to us and are used often enough that we might want to commit them to memory, or at least, have a greater familiarity with them. So, there we are. Those are the ones that are listed in most textbooks as the ones that are probably a good idea to have a familiarity with, okay? Now notice that all of these wind up having the radius of convergence on the right-hand side. Now notice that these right here are different. This one, this one, this one, and this one all have a radius of convergence of 1 because these three were actually derived from that original one. And remember that when you manipulate an existing power series, basically the radius of convergence is related to the original. Now, how do we know that the radius of convergence on these is an infinite convergence? Meaning that you don't have to stay between -1 and 1 in order to actually have this power series give you a legitimate value of e to the x. This power series is going to mimic e to the x whether you plug in 1/2 or whether you plug in 5,000 1/2, okay? So what you can do is you actually can do the ratio test to confirm the radius of convergence and also, thereby the interval of convergence as well, being all reals. Let's go ahead and just do it for sine x, and of course that will give us the tools if we want to at a later date to actually perform it for cosine x and e to the x. So let's go ahead and do it for sine x. Now we know that sine x is n is equal to 0 to infinity of -1 to the nth x to the 2n plus 1 over 2n plus 1 factorial. Now I know that I'm going to be taking the absolute value of it anyway, so when I actually list my a sub n plus 1, I'm not going to include the -1 because it doesn't really matter, okay? So I know that if I plug in n plus 1, I'm going to have to distribute the 2 across that, and so my a sub n plus 1 is going to be x to the 2n plus 3 over 2n plus 3 factorial. Now when I set up my limit as n approaches infinity, you should get a general idea of what exactly is going to go on here. 2n plus 3 factorial, and then of course I'm going to divide by the original a sub n, which means multiplying by its reciprocal. Alright, well let's go ahead and do a little cancellation. I know that this has 2 more than this one, so if I'm going to cancel this out, this becomes x squared. I know that this right here can be 2n plus 3, 2n plus 2 times 2n plus 1 factorial, and of course that cancels out with that. So what I have left over in terms of my limit is the limit as n approaches infinity of x squared over 2n plus 3, 2n plus 2, and that, of course, as n approaches infinity, is going to be 0. And remember, there are only 3 possibilities for convergence. Either convergence converges at a point, it converges at a finite interval, or an infinite interval. And it converges at an infinite interval when what gets spit out by the limit is always less than 1. 0 is always less than 1. It is not dependent upon a particular value of x to continue to be less than 1, and therefore this is convergent everywhere. Okay, which means that my radius of convergence is infinity. And you can perform the same exact thing with the power series representations of e to the x and cosine x to confirm that those have a radius of convergence that is infinite as well. Now, what we have done thus far is we have basically taken the general concept, and I've introduced the general concept of deriving a Taylor Maclaurin series, and I've given you the formulas. In the first video, we used it in order to actually formulate the power series for sine x, and I even sort of hinted at sort of the manipulation of an existing power series can now be done with sine x because we now know sine x, right? So manipulating a known power series can be done for any known power series. From there, in the second video, we went ahead and derived, using the formula, the power series, or more specifically, the Maclaurin series for cosine. We then confirmed it by taking the derivative, term by term, of the power series, or Maclaurin series, for sine x. From there, we did e to the x, and from there we talked just a smidge about the radius of convergence of the very common ones that you're going to be running into, and are listed in most books as sort of a recommendation for what to memorize. That brings us pretty far along. Okay, in the next video, what we're going to do is, now that we know how to formulate these large infinite polynomials that can be used to mimic, and I don't mean mimic in the sense of sort of approximate, I mean mimic as in mimic very, very precisely, as long as we're within the interval of convergence. So basically, this isn't just an approximation of sine, this is sine x, as long as it's the entire polynomial. This does not approximate cosine x, as long as it's the entire infinite polynomial, as long as it goes off to infinity, this is cosine x. The question is, now, can I use these to properly approximate these functions by having a finite series? So instead of having an infinite number of terms of this variety being the actual value of sine, how good of an approximation do I get if I use the first, I don't know, 10 terms of sine x? Well, it stands to reason that I'll get a pretty good approximation. And this is exactly how your calculator gives you values of sine x. It doesn't have sine x in there. It has basically a truncated Maclaurin series. And it basically uses however many terms the people at TI have deemed appropriate to give you an approximation that is good to 8 or 9 decimal places, or however many your calculator shows. So this becomes rather relevant, okay? So in the next video, what we're going to do is, now that we've talked about Taylor and Maclaurin series, we're going to extend that, and we're going to be talking about truncated series, what are known as Taylor polynomials, that are used oftentimes to approximate functions like sine x and e to the x. And then we're going to evaluate those approximations and talk a little bit about error calculations for those Taylor polynomials. Okay? So that's something to look forward to in the next video or two. If you have any questions, as always, please do email me. Bye.